Welcome to our second learning how to approach session for second group of ATSV. So this time, again as we did last time, we are going to be covering a question from lead code, and this was selected by our assistants. And the question is called merge K sort lists. So can somebody share it in the group? Or let me do that. Okay, now let's take a look at the problem. You are given an array of K linked lists, and each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. I think the question is pretty simple to understand. So we are given multiple lists which are already in order, and our objective is to return one list in the end, which is going to contain all the numbers that are coming from these lists that were given in the input. So let's take a look at the example here. Is it visible for everybody, or should I make it a little bigger? For the people at the back especially. Are you guys able to see it? Bigger? Okay. Let's make it bigger. How about now? It's good? Okay. So let's take a look at the sample input here. The given lists we have are 1, 4, 5, 1, 3, 4, and 2, 6. And once we merge them all, we have 2 1s, 1, 2, 1, 3, 2 4s, 1, 5, and 1, 6. So is the question clear to everybody? Now that we get the idea, the next thing we should check is the constraint. So K is the length of the list, and it is going to be less than 10,000. But it is also possible to get an empty list. Let's be careful about that, because on this end it says 0 is less than or equal to K. What else? So each of these lists will have 500 elements the most. Meaning we can have up to 500 times 10,000 elements. So 500 times 10,000, this is 5 million, right? Is it? 500 times 10? Yes, it's 5 million. Yes. And all the elements in the list, they are less than 100,000. Oh, actually, we are not going to have more than 10,000 elements. Because in the last constraint, it says the sum of list length won't exceed 10 to the power of 4, which is the total number of elements in all the given lists. So instead of thinking of 5 million, we are going to be thinking of 10,000 because of the last constraint. There won't be more than 10,000 elements in total. All right, so at this point, let's consider how would an exhaustive search would look like. Like, if we want to take a brute force approach for this problem, how can we solve it? Like, one idea that comes to mind is we can go over all the first elements of the lists. Like, basically we can place a pointer for each of these lists and then get the minimum element of those. And then get it to our output list and move that pointer one further and then do the same check again. So let's try to simulate the algorithm here. So the lists we have are 1, 4, 5. 1, 3, 4, and 2, 6. So at the beginning, we place a pointer at the beginning of each list. And then we check which one is the minimum. Let's say we have 2 1s and the order doesn't matter. We can get any of them. And since we found out this is the minimum, we put this to our output. And then we move this pointer to here. So now we do the same thing. And this time the minimum comes from here. And this guy is moved to here. We do the same thing, we get 2. This guy is moved to here. We do the same thing, we got 3. We do the same thing, we got 4. 5. And then 6. And once we exhaust all the lists, it means we are done. Is everybody clear with this approach? Okay, so now let's see what is going to be time complexity for this approach. We have how many lists? Up to 10,000, right? There can be up to 10,000 lists. Let's check it from our constraints. List.length It can go up to 10,000. So we can possibly have 10,000 different numbers to check against each other. And in order to find minimum element of all these, if we do the check with a linear search, how much time is it going to check? Is it going to take? Like we have 10,000 lists. We are considering one element from each of these lists. How much time would it take to find the minimum? What's that? O of n, right? We are going to do the linear search. Since we have 10,000 elements, it's going to take 10,000 time to find the minimum element, right? And how many times do I have to do this? How many elements do I have the most? 500? Are we sure? But let's not forget that we need to exhaust all the elements. Like one list can have, let's say, 500. What is the limit of 500, by the way? I think each list can have 10,000 elements too. Oh, okay, so each list can have 500 elements. But if each list have 500 elements, still, like, we may have to get multiple elements from the same list. Like, look at the execution of this algorithm. Did we print only 3 things here? Or because we have at most 3 elements? No, we have to process all the elements, right? So we may have to do this for all the elements, and we can have at most 10,000 elements. So this is going to bring our time complexity to 10,000 to 10,000 in the worst case. Is everybody able to see why this is the case? With the approach we have in hand. Like, remember what we were doing. We started from the beginning of each list, right? Getting the pointer to the beginning of a list, you can say it's no cost. But then we considered all of the elements to choose the minimum one. And this took number of lists time, which can go up to 10,000. So at each step, in order to print an element to our output list, we need to consider 10,000, up to 10,000 elements, right? So that's where the first 10,000 component comes. So this 10,000, choose the min from each list. From each list current. Does that make sense? So at the beginning we tried to get the minimum, right? Everything was at the beginning. And we looked them all to find out which one is minimum. And once we print it out, next thing we do is again looking at the pointers and trying to figure out which one is the minimum one. So every time we print an element to the output, we do a 10,000 lookup basically. And how many times we do it? We do it for each element. We do it for each element. That's why we have this multiplier. Does that make sense? So now, is this within our boundaries? No. So up to what point we can say it's within our boundaries? Any suggestions from first group members, like to your experience, in order to get past with an n-square algorithm? Where is usually the limit at lead code? Around 10,000? Okay. So it is around there. Let's say we want to be sure. So maybe we can say up to 7K, 8K. If you don't have any kind of pruning, maybe n-squared is going to work. But for this problem, if we can find a better solution, why not? Looks like we are not in the safe range, right? The 10,000 square, it's a little bit, it may be above the time limit. Okay, now let's think about more. If we can find a better solution here. So, we have 2 components that we can improve on. Is it possible to produce the output list without passing all the elements? Do we have to process every single element to produce our output here? Or is it something we can avoid? It's a Boolean question, guys. Did you guys get the question? Is there anyone who has an idea? Do you have an idea? Felt like you were raising your finger.
What you're saying is comparing every first element?
No, I didn't say anything about comparison. The question is about, is it possible to generate the output without processing every single element in the array?
Yes.
How come?
We only have to process the first elements
And that's it, so the second elements, they will never appear in the output.
for the first time. We don't require to print the first element in the answer.
The question is to generate the output though, like to have this output. Is it ever possible to not process all the elements? I mean, eventually we have to place all the elements into output. Without processing it, how are you going to be able to place it to the output? There is no way you can do that. So that's why we are not going to be able to do any improvement from this end. Does that make sense? So guys, when we are approaching to a solution to make it better, you can use that kind of framing. Because there are different components of the solution that can be optimized further. And some of them, you may not be able to do any further optimization because it's already in the best possible way. And here, what we are considering is there are two main options. We are choosing the minimum element in the first part, and we are doing it until we exhaust all the elements in the input. So now we took a look at the second part. Is it ever possible to produce the output without processing all the elements in the given list? And the answer is no. Because all the elements, they have to appear in the output. Like if the output was subset of it, let's say on a different question, then we may be able to say, hey, indeed we can do some improvement here. We don't have to consider all the elements because if an element has a larger element in the same list, let's say, we don't have to consider that one. If that was the case, then we could have gotten rid of this complexity or improved on it. But now, what we are realizing is, all the elements, they have to be processed. So there is nothing to gain from this component. We are going to be processing all these elements anyways. Does that make sense? Cool. So the further improvement that we can do can take place in this part then. What are we doing here? So we look at the pointers we have in each list. And let's say at the beginning it was the situation, right? And we are trying to choose the minimum one here. So when we are trying to choose the minimum one here, what kind of data structure you think can be handy? Heap, right? Heaps can be handy, min heaps can be handy here. And indeed, there is one more thing. Like as we progress in the algorithm, let's say we get this one down to here to our output. Our input is dynamic. So this time we are trying to choose minimum from 1 to 4 instead of 1, 1, 2. And are heaps supporting dynamic operations? Meaning, is it easy to remove things and add things into a heap with a reasonable time complexity? The answer is yes, right? So, this actually points us in the direction of looking, hey, this part indeed can be solved with a better approach. We don't have to do the linear search to find the minimum element all the time. So, what if we insert these elements into a heap? And let's see what is going to happen. So, at the beginning, in our heap, we have nothing. And then we start from this guy. From the first list, we get 1. And from the second list, we get 1 more 1. And from the third list, we get 2. So, since this is a min heap, my heap is going to look like this, right? And then what is going to happen? And then I'm going to get the minimum element from here. Because that element deserves to be appended to the output list. And I got this one, and I put it here. So 2 came up here. Is this a min heap now? Nope. Therefore, what we are going to do is, we are going to apply down heap to this guy, and it's going to get to this point. So, there is one last thing that I should do. This pointer moved here, right? Now I need to get this new guy into my heap, because it has a possibility of becoming the minimum element. among the ones that I have in hand. And after that, I'm going to do the same operation. So I'm going to put this one to my output, and I'll get rid of this node. And then 4 is going to come up here, and since 4 is greater than 2, in order to keep my heap property, they are going to be swapped. And this is how my heap is going to look like. And this time, since we get this one out, this pointer is going to move to here, and that tree is going to be inserted to my heap. So this is how my heap is going to look like. And then I'm going to get the minimum. 2 is going to be printed out. 3 is going to come up here. This node is going to go. And since 2 was printed, this pointer is going to move to here, and then 6 will be inserted to my heap. And I think the rest is easy to follow, right? Okay, so now let's see where did our time complexity come to. So I have a heap here. How many elements can I have in this heap at the same time the most? 10,000, right? What if I have one element in each of the lists? Then all of them are going to be inserted to this heap, and I'm going to have 10,000 elements. So every time I remove and add an element to heap, how much of a time complexity do I get? Log n, right? So in order to print out an element to output, or append an element to output, how many add remove operations do we do? We do one add and one remove, right? So basically every time the operations we do, it takes 2 log n. And where n is here 10,000. Or let's go with n for now. And how many times do we do this? Number of elements times. Is this going to be our total time complexity then? Is there any other operation that we should do? Appending to a list should be pretty simple, right? O1. So we don't need any other operations actually. So that's going to be it. So how about now? N log m, is it good for 10,000? It's very good, right? I mean, log n is less than log 10,000. I think it's going to be in the order of like 10, 11, 12, 13, I guess. 13 times 10,000, still we are under 1 million, which is pretty good. It should be pretty fast. So at this point, can we do any further improvements? We have n log n here. Maybe with this solution we may not have some other improvements, but there is one more thing that we can take a look, which is the range of the numbers. What is the range of the numbers? From minus 10,000 to 10,000, right? By the end of the day, I am supposed to return a linked list which has all these numbers in order, right? Does it care about, hey, you have to bring them from the initial input lists? Like it has to be exact that node object. It doesn't have any such kind of requirement, right? If I am only interested in producing an output result in which the elements are going to be in order, what can I do? Nice. If our range fits well, we can do counting sort, right? Can we apply counting sort directly to this given range? Nope. But what can we do?
Put also the value for the negative numbers and sort them in the multiplier for this counting sort.
That's one thing we can do, but they are going to overlap with the positive ones if we just multiply them with minus 1.
Then no, separate negative numbers and positive numbers. Then we find the absolute value of the negative list.
I see. Yes, that would work, but it's kind of like this.
Yeah.
Can we find a better solution?
We can map the negative ones. Like, for example, let's say our range is minus 10 to positive 10. We can have 21 numbers, which we can map the negative ones to the after the 10.
You can just shift the range,
shift the range.
by how much you need, like which is here minus 10,000. Like our range was from minus 10,000 to 10,000, right? What if I move this to the right 10,000? Then my range is going to be from 0 to 20,000 plus 1 or 20,000. Probably 20,000, yes. Since if we want to keep 0, yes, 20,000, yes. And then we can get an array for that, right? And apply a counting sort as we know. So if we do that, what is going to be the time complexity? What is n? What is n?
Number of total nodes.
Number of total nodes.
I mean, first we have.
Yes, like assuming they all have different numbers, right? Yeah. Yes, like we can say 20,000, right? Since we moved the range, like we are going to be checking all the cells. It's going to be 20,000, but it's in the order of n. Like 2n is n, so we can say O n. So is this more efficient than n log n? Yep. Right? But this time, in order to get to this solution, we had to change our approach very dramatically, right? At first, we were approaching it in a very different way. Hey, let's go over each list, let's get the minimum element here. And we were like, okay, so we can do this linearly, but looks like we can also do it better with heap. And that's how we get to the n log n solution from n square solution. And at this point, further improvement didn't come from making changes to this solution in hand. So we stepped back, and then we took a different look. Since the range of the numbers we are dealing with it was very little, we were able to apply counting sort here, right? And once you have counting sort, you can easily generate your output as a linked list like this. So is everybody clear with both approaches that we have considered up to this point? Indeed, we considered 3 approaches. Okay, so now shall we go ahead and implement them? So I guess everybody is clear with the algorithms, their time complexities, and we have confidence in the accuracy of our algorithm, right? And it means this is a good time to jump into implementation.
Yeah,
And before getting to this point, if you do that, it may be a little too early. So you may say maybe a few minutes, but by taking the risk of maybe going in the wrong direction for 15 minutes. And which can be the difference between getting accepted or getting rejected in an interview. Cool.
Yeah,
Yes.
Since you mentioned like the difference with the counting sort approach could be the having extra memory.
Yes.
Counting sort approach.
Yes. And but we are going to also have a heap, right? It kind of has an extra memory too. So yes. But yes, there is an additional
So if
extra
you do it
memory.
in
We didn't
place-
talk of memory. Yes. Thank you.
In place can happen.
Cool. If there are no further questions, we can jump into implementation. Alrighty. So for counting sort, let's start with the counting sort approach because it's easier to implement. And what we are gonna do is we are gonna have a vector counts. And the size of it is, let's say 20,000 one, and we will initialize it with 0. Was it like this? Vector initialization. Okay. Cool. Is it size? Since it's a vector, it's size, right? It's plus. And yes. How about now? Like this?
Yes, perfect.
Okay, perfect. And what we are gonna do is we are gonna say counts lists. Oh, we need one more for loop actually. We are going over all the lists and we will be going over each element in each list. So we'll have a secondary for loop which is gonna traverse over the elements in the lists I. That's also vector.
You need to create a list.
Oh no, that's actually, this is not going to be a for loop. I think this is going to be with the list node. Let's say node. This is equal to list I dot list I. This is a vector, right? No, list I, this is a node. So this should be it.
Yeah, it's the head of the first.
While it has next, node is equal to node next. Okay, and then or actually we can say while node. Yes. And inside what we are gonna say is count not val plus plus 10,000. It was the limit, right? We need to shift everything by 10,000. Yes. Okay, so once we do that, we are going to have all the counts. And then it's super easy to generate the output, I guess, right? So we can say, like we are going to return the list node. Star result is equal to new list node. So we are gonna go over, at the beginning we generated counts in 10,000 shifted manner. And then we will start from the beginning and then see if there are any elements in that bucket. While count I is greater than 0, I will continue doing something here. And what I'm gonna do is I'm gonna add the node to my new list. And I'll say result, well, yes.
Did you zoom it?
Zoom in? Sure. How about now? And I'll say the value is gonna be result val is gonna be I. And we are gonna create a new node. Result next is equal to new node. And then we are gonna move result to result next. So is everybody clear with these operations? Like since those are linked list operations? Like in C++, we are using arrows because of pointers, but in Python it's gonna be a dot, I guess, right? But it's the same logic. So you guys should be able to follow it, right? Any questions up to this point? Are we clear with everything? Cool.
One question.
Yes.
If the number is negative right now.
So there is one thing that we forgot to do here, which is decreasing count I. Indeed, there is one more thing. The results value is not going to be directly I, but we shifted it by 10,000, right? We added 10,000. Now we have to pay it back. So that's why we add I minus 10,000 to the result. Does that make sense? Like in order to get rid of the effect of negative ones, because we cannot have negative indices for array, right? We shifted everything to the side, to the right by 10,000. So that the minimum value we can have will be 0. And now when we are generating the result, we have to pay this cost back. So that's why now we are decreasing the value that we have in count index by 10,000 before putting it to the result. So let's say if it was 1 at the beginning, if the node value was 1, then we were increasing 10,001 here. And when we are placing the result, once we count to 10,001, we are going to see some value that is greater than 0. That's why this while loop is going to be executed. And when I is equal to 10,001, we actually mean value 1, because everything was shifted by 1,000. So that's why here we are subtracting 1,000 from I to decide on what is going to be the new value. And after we assign the value, like if you see here, at the beginning we generate the place. So we have one node that is empty, that is waiting for the result. And once we found the element, we placed it in, and then we move to the next one. So is everybody clear with everything here? Cool. So, team, there is one thing that less experienced programmers would make mistake. So many less experienced programmers would just leave it here without doing the proper cleanup. What are we doing here? Like as you see, at any point we always have one empty node at the end of our result linked list. At the beginning we just start with an empty node, right? It has nothing in it. And once we add new things, what happens is we just create a new empty node by the end, and it gets filled if there is one more element that is coming. What is going to happen by the end? when we add the last element, when we see count I that is greater than 0, like this means this is greater than 0 in C++. That's why you can write both ways. To make it more clear, let's do it this way. So once we write the last element will add its value into the result. But it will also create this new place, new node, new empty node at the end of the result. And if we don't get rid of this, obviously our answer is going to be wrong. Because I don't think they expect to have one empty node by the end. So is everybody able to see here why this would be problematic? So what we should do is once everything finishes, here we should indeed make result next now.
Result must be there.
What's that?
Isn't that the result must be there itself? Why not next?
You are making a good point because we also moved the result to the next one, right? So the result is currently pointing to the node. Yes.
And one thing is like this, what if we create dummy node at the beginning, then we start the node, append the nodes to the next, it will be easy, then we just need to return the dummy nodes directly.
Well, if you do it that way, you are going to lose the order. But you can process the list in the reverse way. Like, but still, you're going to face with a similar problems you have. So now, let's see what is the expected behavior in case of empty input. Okay, oh, it also has those examples. So the output must be empty. What does that mean though? Like, it's not null. Is it null?
It's not. An empty linked list is not.
An empty linked list is null. Okay, cool. Alright, so now let's see. Currently, we didn't address this problem well yet. This is not the action that we should take. Basically, what we want to do is we want to do our previous node's next null. Because if you do, let me show it here. I think it's going to be more. So the situation we have right now is, let's say we have 1 and 2 in our result. And result is pointing this. If we make result now, what is going to happen is, result is going to start pointing now. But this node will stay here. So what we really want to do is, we want to make this guy's next null. Does that make sense? So in order to be able to do that, what we can do is, instead of always keeping track of this empty node, we can also keep a pointer in the previous one. This way, yes.
What if we only keep a pointer to the previous one?
What if you only keep a pointer to the previous one? That should work, but at the beginning you don't have that.
You can start with the dummy.
Yeah, can I show?
You can start with the dummy one and we can remove it at the end. That makes sense.
You don't need
Yes.
to remove friction.
You can just return the next one.
Yeah.
Yes. Okay, so let's do that. Alright, so result is the empty one and we are going to be placing here into results next. So we created the results next node and then we are going to say result next value is this.
Actually, why not move it earlier? Since you already know it's going to have a value, you can, instead of having to say I got the next plus value, move result.
Yeah. Current. And we are going to have this node result is equal to current. And then we are going to be moving the current one. Yes.
Can we not just do it while the count is greater than 1? And when it gets out of that loop, we'll just make the next one. Once that we...
Yes, that should work too, because we know the total number of elements. That should work too. I guess, yeah, they are pretty similar to each other. Yeah. But, I mean, there are multiple ways of doing the same thing, right? So you can choose any, but we have to do one. We have to do the cleanup, because if we forget about cleanup, we are going to produce the wrong result. Okay, so now we get the result and
Can't we pass the attributes in the constructor directly? And then
Yeah.
if it has such,
Yeah,
let's
you
see.
can directly pass the values.
Okay,
Put the value in the next step. Yeah.
okay, so
The value will be the I minus 1000. The next would be
like this. Yes. And by the end here, result can have this empty node in it, so we should check. But is it 0 by default? The value is 0 by default. Okay, so now result has to be the next of result, right? And it should be null if it is empty, so this should fix it basically. Or we can just say return result next. This will be clean. So what do you guys think? This should do the job. Let's see. Oops, really? All right, here's the code. Oh, list node. So this guy should be a list node. Let's give it a try again. Yes. And let's try an empty list.
There's the example.
Yeah, there's a button you can use example test case.
Okay, so it tests all of them. All right, let's give it a go. Like normally we would test more test cases, right? But since we are gonna try different approaches here, that's why we will be going faster. All right, so is everybody clear with this approach? Now we get the idea, but as you see in implementation, since it's asking for a linked list to return, it made us think for a while, right? Cool. So now let's go to the second stage. What is the second stage? In the second stage, we are going to be implementing the heap solution because we want to get more experience with heaps. And indeed, we are going to progress to the third stage if we have time after. So in the second stage, we are not going to be using this approach. Let's get rid of this and this and this and get back to here. So let's have this code as counting solution, and it's ON.
It's already submitted to you.
Like by the end, we might want to have them all in one file. That's why. Okay. In the second one, we are not going to need counts vectors. So we are going to be processing them. We can keep this part, but we are not going to be initializing counts. Let's see what are we going to do. Okay, so when we are placing them to the heap, do we need to keep any kind of pointer back to their lists? Like what are we going to keep track of? First off, we need to know our position for each of the lists, right? So we should generate an array for positions or vector for positions. How many lists do I have? I have list.size lists, right?
Yes.
And I want to initialize all the positions with 0. At the beginning, we are at the beginning.
But these are linked lists, right? They all have indexes.
Can you zoom in and move in?
Okay, so instead of using int, I think it's better to. Oh, indeed, we can. We already have it. Like this basically is it. So we don't really need to. Yes. Zoom in again. Sure. How about now? Better? Cool. All right. So we are gonna go over the list, and at the beginning of the list, like once we do next. We don't really have to go back because once something is inserted to heap, we don't really care what is going to happen to our input. So we can definitely make progress on the list. We don't need to build anything for that. And we need to get our priority queue. So priority queue is a heap. And what are we going to keep in this? We are going to keep the number, but do we need anything else? Think about it.
Counts. Oh, sorry. No,
The node itself isn't enough.
The node itself, yes. So we are going to need the value, but the node itself will not be enough because if you give the node, then you have to give the comparator as well. But if you give a pair, by default it's going to sort it by the first one. So that's why we can make it an int and node pair. But in theory, yes, the node itself would be enough. So we can say int and list node. It's not pointer. Yes.
Ever you have to take pair first.
Yes. This is a pair of int and list node. And let's say it's going to be called heap. All right. And what are we going to do here? It's less than list size. Yes.
This is by default massive in C++.
So yeah, we can just insert the values with negative, like multiplied with -1, and it's going to be a mean heap. So that's okay. All right. So now the next step is how are we going to do the process? So what is going to be the initial state of my heap? So now it's empty, right? But how do I want it to start? Try to remember the algorithm. How am I going to make sure that the first element that I'm inserting into my output is the smallest element? In order to guarantee that, what should I have in my heap?
Positive.
What's that?
Positive.
Positive infinity. For what?
For the minus.
I don't think. You can just basically start from the first list, first value, since it's already sorted, right?
Yes, it's already sorted.
Since it's also smallest.
How do you know that it's smallest?
Oh.
The head.
What's that?
It's pointed in the head, starts in the head. It's the smallest element in that linked list.
It's the smallest.
But in that link.
In that linked list, it's the smallest element, yes.
You have to iterate over each element and insert your heads value.
Each element? Or?
It's heads, maybe the heads.
Yes, yes, that is the answer I was looking for. So basically at the beginning we need the heads of each linked list in our heap. That's the only way we can guarantee that the smallest element will be in the heap and the minimum element at the top of the heap is going to be the global smallest. Because if we don't get one element from each of the lists, we cannot guarantee. If there is any list missing, maybe that list minimum element was smaller than what I have in hand, right? So that's why we have to include one element from each list at the beginning. And that's why what we are going to do here is we are going to go over each list and then we are going to say heap dot, is it insert? Push? I guess it is push. Okay, push. And we are going to make pair out of what? Out of the list I value times -1 and list I. Does it make sense? Cool. Now let's keep going. So we are not going to have such kind of a loop, but we are going to have a while here instead. While my heap has an element, while our heap is not empty, we will go inside. And we don't have any count condition anymore. And here we are gonna get the new node from the heap. So we can say, like we are gonna get a pair of an integer and a list node, current, or let's say naming is sometimes difficult. Current pair. And this is gonna come from the heap and it's gonna be the top element, I guess. And then we need to call pop as well. So that's one thing also you may forget, depending on your choice of language, you may need two different functions for top and pop. And don't forget to call the pop as well. And after that, the current next is gonna be new list node, and the value will come from not I minus this, it's gonna be current pair, that's second. Well, and we don't need something like this. Okay, so there is no this, not this for loop. And now, okay, so we are cool with getting the element and adding it to the result, but is this the only operation that we are interested in? What else should we do here? Anybody? Pop, we are already doing it here. Maybe let me make it more larger. Like here we are already popping it. So we pop the element, we put it to the result. What are we supposed to do next?
We have to push it back.
We have to push the same thing back?
No, after we update the pointer, right?
What's that?
Since we updated its pointer.
Where did we update its pointer? Like basically what we are gonna do is we are gonna move that list current pointer to the next element, and that next element will be inserted to the heap. So the next element is in the second of the pair, right? Current pair, that second is equal to current pair. That. Or do we have to keep the list ID? Do we have to make the move from the list? Because the pair is going to have a different pointer, I think. Let me think about it. Are we directly putting the element? Yes. Oh no, we are putting directly the element, so it should be the same thing. Current pair equal to current pair, but second next. Does it make sense? Is everybody clear with what we do here? Like basically, we get the minimum element from the heap, right? And if you remember our process, when we get an element from a list, we need to move the pointer. Like let's say we get this one from here and then we put it to the output, then we move this pointer to here, right? And in this input, it was coming with the list, and this first element was this. And once I place one to the output, what I want to do is I want this pointer to show up to 4. And I want 4 to be inserted to the heap too. And lastly, that's what I'm going to do here. So here we are going to insert this guy now, like heap that's, or indeed we don't even have to do this move. Like if it has the next, then we can just insert the next to the heap.
Yes, exactly.
Should be fine enough. So heap.push, we are going to say current pair that second next, if it exists, of course. Yeah, we are going to make a pair, so I'll update this. Second next.
Emre.
We are going to make a pair of this guy's value and this guy itself. So is everyone clear with this part? What we have done here. So here, get the min elements, get the minimum, element from the heap. This is what we do here. And then add the minimum element to the result. And here what we do is add the next element from the list that the minimum element came from. From the list to the heap. Or let's make it this way, it will be more readable. To the heap. Does it make sense? So are you clear with these different steps? Okay. And is there anything else that we are supposed to do? Like once our heap is empty, we are just going to return the result. Right? Shall we give it a try? All right. Undefined behavior sanitizer. Undefined behavior. Oops. What's that?
Null value.
If it's, yeah.
It's a null pointer.
If it's, the list is not.
Okay. If because some of the lists can be empty. And if the list is empty, then yes. That's a fair point. And also I think we should do a similar check here. Oh, actually we are doing it here. We check if the second exists, then if the next exists, then we do the push. Yes.
By the way, before that remapping the result, we have to multiply with negative one.
Yeah,
Oh, that's very true. So basically when we are adding them to the result here, well, we are getting the value directly from the node. So we basically make the change for the value that we are creating the heap on. But the value that was not is preserved since we get it from there. No need for that. But yeah, normally we would have to. Yes, so now let's take a look. No matter what, we are returning an empty result right now. So if our heap is not empty, what we can do is we can print our heap size here. So let's give it a go. 3, 3, 3, 2, 2, 2, 1, 1.
Emre,
Yes.
since we are, I think, modifying the keys while inserting the nodes into the heap, I think we should also multiply one into heap one.
Yes, here we should multiply it with -1, but that's not the problem that we are dealing with at the moment. So that's a good catch. But let's see what other problems we have. First. Top one. Topped. And Tim, when you face with an error, you should feel comfortable debugging it with prints. Because we don't know in what environment you will be doing it, in what language you are going to be doing it. So there are different debuggers for different languages. But there is one thing for sure that is available in your favorite programming language, which is you can print things to the screen. And if you get good debugging skills early on, this is going to help you a lot in your career in the future. Because majority of the time, you're not going to write everything perfectly from first try, right? There will be some bugs, as in the case of this one. And then you will be debugging your code. And this is okay. This is part of our job, but we should have very effective debugging skills. It's very important in the long run. And even in the short run, like. So now let's see what is going on here. So we popped -1, -1, -2, -3, -4, -4. So these are 1, 1, 2, 3, 4, 4, 5, 6. Indeed, everything is working from the heap perspective. So I think we have the problem when we are generating the results. Let's see. So we say current next is equal to new list node. Current pair dot second value. So now let's also print here the current. Current. And we are going to say current next value.
It's not good always must have. That's
What?
we are calling next and then
So this one should be current. One, 2, 3, 4, 4, 5, 6. So that is also. Wait, our output is equal to expected, no?
Says accept.
It says accepted.
Yeah.
Was it accepted since the beginning, or?
It was the problem was the thing that I mentioned at the minus something. Then it says accepted.
Okay. So it was running multiple input at the same time. That's why I was misled. That I was thinking we are only producing empty output. Okay. Now I see what is going on. Cool. So we didn't have any trouble with heap basically. Okay. But it's nice to see some print debugging. All right. So now let's get rid of our debugging codes. Because like this part was working in the first code, right? I was very surprised. Like, what did we break? Okay. So now let's give it a go. We still print something out. Let's remove the last cout. Okay.
One more.
One more? You sure?
Yeah, individual. 57. Yeah, it's not.
Where is it?
K, yes.
0. Okay. And let's give it a go. And it's gone.
Zoom out.
Zoom out. You sure?
Yeah, it's on the left side right now since we closed. Yeah.
Okay.
Gives.
All right.
Gives box.
Looks like, I had an old code in the past, a Python code. Let's see how it looked.
I think the language is different.
Okay.
Deepak.
He pushed it. Looks like it's the same thing.
Compass.
All right. So, team, yes. Any questions?